Hello, everyone. Welcome. Thanks for joining our diagnostic training session today. And what you're about to see is a pre-recorded training session we did over in the United States. But be assured that a lot of the material that we cover is really applicable to any automotive application. So just be aware that yes, it is a lot of North American vehicles, but they will apply a lot of the same principles apply over in the UK as well. Now, if you do have any questions, if you're watching this during the premiere, you can just leave it in the chat. We'll be monitoring live chat. If you're watching this after the premiere, then just feel free to leave a comment underneath the video and we'll get to those as we can as well. So my name is Jason Gabrenas. I'm one of Snap-on's diagnostic technical trainers. I've been in the training department since 2013, traveling around North America, helping techs and shop owners get the most out of their diagnostic equipment. Before I did that, it was a couple years as a diagnostic sales rep at Snap-on, so I had 30 different franchisees I worked with, as well as the shops that they serviced, in order to help everyone get the most out of their diagnostic needs. Then before I did that, it was 8 years at Subaru. So I worked in a dealership, and over time, I guess, just became the default diag guy in the shop. So I always ended up having the drivability problems, the intermittent problems, the weird wiring problems that would show up on those cars. And that's really where I cut my diagnostic teeth, was trying to figure out all those weird head scratcher type cars that would come into my bed. Then before that, a bunch of other miscellaneous wrenching jobs. Been a little over 25 years under hood experience for me. So our topic today is guided component tests and how they tell the rest of your diagnostic story. Now, this will be our intro to guided component tests course that we'll go through this evening. So if we think about our scan tools that we have, or our diagnostic tools, we have scanners and we have scopes. When I like to think of a scanner, I like to think of it as a really nice compass. It's going to point us in the right direction. It's going to show us where we need to look, where we need to go, but it's really only showing us part of what's going on with that vehicle. It's really showing us the effect. And for every effect, we need a cause, right? So in order to find that cause, that's really where the scope or guided component testing comes into play. So if we think about a vehicle, let's think of it like a house and the PCM of this vehicle. It's like a house. So it's got a front door and it's got a back door. So coming in that front door will be all my input signals. So my knock sensor, my coolant temp sensor, my oxygen sensor, all those input signals feed through the front door of the PCM. The PCM then processes it however it's programmed to do that. And we know sometimes that cannot be correct because, well, we have reflashes, and that's why reflashes exist, to change how the PCM interprets things sometimes. But it goes through and it processes it, and then it takes that data stream and it sends it out the back door as a processed data stream and presents it to the scan tool. So if we're only using scanner data to look at this signal, we're only looking at this half of the equation. We're really only looking at half of what's going on. We also need to be able to check our signals and verify our signals coming into the PCM to make sure they're even good in the first place. And that's why we need component testing. Two different types of diagnostic tools is dictated because we have two different signals, right? So anything coming in that front door, that raw data, that input data coming in, we need our guided component testing. And then out the back door, any of that effect, that process data stream hooking up to the DLC, well, of course, that's where the scan tool comes in. Some tools have both combined. You might be thinking, well, why not just rely on the data, right? It's a computer just telling me what's going on, right? So it's, as far as the computer knows, that's what's going on. If we think back, we've always used data way back since even 30 years ago, right? When we first came out with the MT2500 at Snap-on, that red brick, all right, way back then. And if we were looking at the data stream on one of those tools on an older car, we would see numbers on a screen, and that's all we could get was numbers. And if we were really lucky, those numbers might change once every second, once every couple seconds. Right? So the data speed on the cars back then weren't all that fast, and granted, the tool wasn't all that fast, and it didn't have to be anyways because the cars weren't all that fast. And you might be lucky to have 5 or 10 PIDs on a car, and that's about all you had. So nowadays, though, these faster sensors, these more advanced systems on these cars, those numbers on that screen can be changing 10 times a second or faster. Now, I don't know about you, but I have a hard time reading things when they're changing 10 times a second. It is valuable data. It's good to have, but often it's too fast, and often it's too much data overload. If we think about some modern vehicles, you looked at the data stream, it could be 400, 500, 600 different data PIDs coming into that tool. Now, we do have ways to filter them down and make it a little easier to look through it, but still, it's often that information overload at this point. So a little bit later, maybe 20, 25 years ago, we decided to take that data, those data points we have, and graph them over time. So that is what a graph is on a scan tool. We've been doing graphing on scan tools. Most scan tools do this at this point. It's a recorded history, right? It's numbers plotted over a period of time. And history is your important word right there, right? It already happened. As we said, it's that processed data stream coming from the vehicle. A lot of people will refer to this as live data. It's not actually truly live. It is that processed data, and it's at least a few milliseconds old, if anything, right? So it's not 100% accurate as to what's coming out of the vehicle. Now, it's not the scan tool's fault. It's more the vehicle's fault, right? So scan tools don't lie. They get lied to, right? It's whatever the computer's telling the scan tool. Well, that's what you'll see on the screen, right? So it is that processed data. Now, it is useful for having this data. You can see trends as are things getting better? Are things getting worse? Are things just completely missing? And also, there are some things you can only see by looking at scanner data. So if we think about misfire calculations, right, that's internal to the computer. Some AF sensor calculations, that's internal to the computer. Things of that nature, sometimes you need that data, right? So it's just another piece of the puzzle, but we don't want to rely on it 100%. We need to add some things. Let me give you a little visual of what we're talking about: scan data versus component testing or scope use, right? So if we look at the screen, top left-hand corner, we have the blue line going up and down. That is graphed processed data on an oxygen sensor on this vehicle, reading voltage. The bottom part of the screen with the yellow up and down line, well, that is a scope or guided component test meter hooked up to the same oxygen sensor, reading the same voltage. Those two red boxes show the same amount of time passing. There is a big difference in those two signals. I think you'd agree. If we look here, there's what the scan tool is telling us, and here's what the sensor is actually doing. We can see the resolution is much more high, a much higher resolution. We see these two little dropouts right there. Well, the scan tool didn't even know that happened. And once again, not the scan tool's fault. It is more the car's fault. So we think about it. Signal has to come in. Car processes it, sends it to the scan tool. Signal comes in, cars process it, send it to the scan tool. Every time that happens, that round trip takes a little bit of time. It might only be milliseconds, but it still takes time. So we lose that resolution in the signal every time that happens. Being able to sample it up to 6 million times per second with a scope, well, that just makes it all the more easier to see that detail. It's like watching one of those 4K big screen high def TVs versus like one of those little portable black and white things you might have in your garage, right? So big difference in the details. That's why we want to utilize that component testing. So we think about a scope. Well, what is a lab scope anyways? Well, really, it's a tool that gives us a measurement as a picture painted over a period of time. So our vertical is our measurement. So voltage, amperage, pressure, what have you, over a period of time, whatever we happen to choose. I like to think of it as a window. It's a window I'm going to look through, and I'm going to see what is that signal doing electrically, right? And when we're changing the settings on that scope, I like to think of that as we're changing the size of the window. So am I looking at more time? Am I looking at less time? Am I looking at more voltage on the screen or less voltage on the screen? We're just changing the size of the window. So if we want to kind of think about it that way, maybe it makes it a little easier to wrap your head around what the changes we're making actually are doing as far as how we're viewing the signal, right? And we'll talk more about that when we go live in a couple minutes. So guided component testing is also your friend when it comes to comebacks and intermittents. Now, I don't know about you, but I'm not a huge fan of comebacks or intermittents, right? Comebacks are the, usually it's some sort of a misdiagnosis, or how did I miss that? Came right back for the same exact problem. It wasn't fixed. And most of the time, those are for free, right? Because they already charged them once and it didn't fix the problem. Then there's also the intermittent problems, right? It happens on the third Thursday of the month when it's 72.9 degrees out, and I've been driving for 36.8 minutes, and it's 68% relative humidity. Otherwise, it's not going to happen, right? So it's those weird once in a blue moon type problems. When it comes to the component testing and the scope, we can catch those little tiny fraction of a second glitches that might happen for those sort of intermittent problems, right? We also need to verify. This is going to be huge for comebacks, especially verify your problem and then verify the repair. Because remember, if we're just looking at that scan data, like we said before, the scan tool only shows us the effect of a problem after it already happened. It's a good clue. It's going to point us in the right direction. It's going to show us where we need to look, where we need to go, but it's still only the effect. We want to make sure we verify the problem and then we want to verify the repair after the fact. If you think about it, if we suspect a component is faulty, let's just test it. Test the component, and if it is bad, if it tests bad, then we can be a lot more confident ordering a new one. And then when you order the new one and install it in the vehicle, before that vehicle leaves your shop, you want to verify that the new part fixed the problem, for one, and two, that the part isn't bad out of the box. Have you ever gotten a brand new part in a box that didn't work? I think it happens way more often than it's supposed to, right? So if we're verifying that we have a failure first, and then we're verifying that what we did fix the problem, that'll cut down on a lot of those comebacks, right? And it also just helps us maybe speed up our process as well. So when we're looking at guided component testing, what we're testing for is a failure, right? We want to test and see, is there some sort of a failure somewhere in the circuit, including the component? And really a failure could fall into, I'd say, these three buckets, right? Let's say first, open. So for an open, perhaps we have no voltage going to a component. So we test for voltage at the component, there's no voltage there. So perhaps there's an open in that wire that is feeding the component. Or maybe we have voltage at the component, but there's no voltage coming from the component to the computer. Perhaps there's an open in that part of the circuit coming back, right? So we would check both ends of that circuit to make sure that it wasn't open somewhere. And then a short. Or we could have excessive voltage. Let's say it's supposed to have a 5-volt reference signal on the sensor, and then for some reason it's getting 12 volts because it's shorted to a 12-volt wire that's sitting right next to it, and they're rubbing on each other inside the harness. It happens, right? So perhaps that could happen. That'd be a short to power. Or maybe we have insufficient voltage, would be short to ground, right? Maybe it's rubbing on the back of the intake manifold, and every time it goes over a bump, it rubs, and then it zaps the power just that little bit, sucks a little bit of that voltage off and feeds it to ground before it gets to the sensor, right? So that's a short to ground. And then we have, could be resistant, right? If you think about corrosion, right? Up where I live, corrosion is a huge problem because we put salt on the roads in the winter, but you know, the green fuzzy stuff on the connector, you pull it apart and oh, wow, look at all that. All right. So corrosion causes more resistance, which causes us to lose voltage. Or damage, right? If we had a damaged wire, if we think about most wires on a car nowadays, they're multi-strand copper, right? And multi-stranded copper wire, well, we could have one or two of those strands still stuck together, but the rest of them are cut, right? Maybe it was rubbing on a sharp corner or something of that nature, in a door panel perhaps, right? And then it would still carry voltage, and we could still test it with an ohm meter, and it would still test good in the ohm meter because we do have continuity, but it won't be able to pass amperage because it doesn't have enough connection there in order to pass that amperage. You'll lose that amperage due to the resistance. All right. So let's look at a case study, real world case study here, 05 Jeep Wrangler. And it's what we'll call an intermittent no start. Now, this isn't the exact Jeep right here, but it looked pretty close to this. You know, it had the big tires, had the big lift kit on it. The customer liked off-roading with the truck, right? So the complaint, vehicle will crank, but there's an intermittent no start. And really, in my mind, I would classify it the other way as more of an intermittent start problem. You could start it 100 times, and maybe once it would start, and then the rest of the time it wouldn't. So it's very much not starting, but you might get lucky every once in a while. The customer had already attempted some repairs, so they had this problem. So they went on the internet and asked their buddies in their Jeep forum or whatever it happened to be. And they said, well, yeah, change the crank sensor, change the cam sensor. Worked for me. So, of course, they went to the parts store, bought the cam and crank sensor, put them in the vehicle, and still had the same problem. So now they're in the shop. So what should we do? Well, where's a good place to start? First thing is, well, we want to see if there's any codes in there, right? Give us a place, give us a good starting point. So here's our home page for the vehicle. If we look at the very top, we have our code scan. It's good practice to start any diagnosis with a code scan, especially when it's a drivability problem, no start issues such as this, you know, what have you. It's good to just check and give it a clean bill of health, or see, are there any codes in there? Because there could be codes in other modules that don't turn on a light. And in those other modules, it might somehow affect the vehicle. Network codes come to mind, right? So we want to make sure we scan the entire vehicle and double check, make sure there aren't any codes. So we'll go in a code scan. We'll do a pre-scan, and no codes. Always fun when we start with that no code situation, right? Now I don't really have anything to go on, so I guess I need to gather more information on this situation. So we see our list of modules here. Now, some folks don't know that there's a shortcut from this screen right into a module. So if you look at the names of the module, engine, transmission, ABS, they're all underlined. Those are all hyperlinks, and they will link you directly to that module in the tool. So I don't have to back up, find it on the menu. I can just click on it from here. So we'll click on engine, and it brings me right to the top of the engine, right? Codes, well, that's not going to do us any good. We know there's no codes. Data, we could look at data, but we might not know what necessarily to look for, right? Functional tests, maybe there's something. But let's go look at troubleshooter. Troubleshooter has a wealth of information in there, and I think it's, could be one of the underutilized portions of the tool. You have all these other things that you could do with the tool. Well, troubleshooter is a good resource. It's been in there for over 25 years. So let's go in there. Code tips won't do us any good, so we don't have any codes, but maybe there's a symptom tip, possibly, could be a time saver. But I see fast track data scan, right? Remember how I said we might be able to go into data, might not know what we're looking at though. But in fast track data scan, that's not on every vehicle, but when you do see it, this will list PIDs for that vehicle and tell you what you're supposed to be seeing. So we'll go into fast track data scan, and we see a list of select PIDs on this vehicle. Now, do I see anything that says cam or crank sensor? Looks like fourth one down on the right-hand side says cam sync, cam sensor status. So let's look at that. We go in there, it gives us a description of what the PID is or what it's trying to tell us and what we should see. So it's, does the PCM see cam and crank signals during startup and normal operation? It is a yes or no PID. So I either see yes or I'll see no when I crank. So we have both data PIDs on the screen at the time as well. So it actually feeds those to the screen, so you don't have to go back into the data to find it. So we have both of those there. So we just cranked it over, crank, 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 crank. No, 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 no. Never changed. Now this is data stream coming off the computer, right? So according to the computer is telling us, I don't see the cam sensor. I don't see the crank sensor. It's not there. It doesn't exist. And that's why we're not starting, most likely. Okay. So we got some good information there. We kind of know which way we can start going, right? So it says we don't see a cam and crank sensor. So let's test the cam and crank sensors, see if they even work, right? That makes sense. And you might think, well, the customer already replaced them. Yeah, but once again, I bring you back to the, have you ever gotten a brand new part in a box that didn't work? So got a component test. We'll go in there, and it is VIN specific information. It goes all the way back to 1981, the material in here. There's over 5 million tests across the board. In this case, on this 05 Wrangler, we see, looks like 8 different categories. There could be up to 12 categories on a vehicle, depending on how it's equipped and what kind of information we have on it. In this case, I want to check cam and crank sensor. Those live in the engine, right? So we'll go in there. It will list the components in that system, or perhaps subsystems if they have subsystems. In this case, crank sensors right there, top right corner. We'll go in there. We could read component information if we want to see how it works. The rest of the information on the screen will be different tests that we can do. Could be 1 to 6 tests depending on what it is. In this case, I'd like to look at the signature test to see what is that sensor outputting, what kind of signature, what kind of signal are we seeing. So we'll click on signature test. We need to connect to the sensor. So there's where we would connect. This is on pin 3, and I'll show you how we knew that right now. So we look at the screen for the test. Top left-hand corner, it tells me that we want yellow goes to CKP signal. So that'll be pin 3 right here, and that's on the right-hand side. And then we crank it over and we see what the pattern is. In this case, it's a 5-volt square wave. Each one of these squares represents one of the teeth on the reluctor wheel on the back of the crank. So there's one part, and then half a revolution, and then a full revolution over there, right? So it goes up, down, up, down, up, down. If we'd scrolled up a little further when we captured the screenshot, you'd be able to see this on the screen as well. It gives us a known good pattern inside that signature test. So this did turn out to be a good pattern. So we cranked it over, good pattern, good to go. So we know the crank sensor's working. Let's back up and try the cam now. See if the cam sensor is working. Maybe that's our problem. So back probe there. Come in here. It says the pattern should show 321, 312 on the pulse, and we actually captured the pattern on here. So 321, 312, 321, 312, et cetera, et cetera, et cetera. Looks like the cam sensor's good too. So we tested the crank, crank's good. Tested the cam, cam's good. Computer says, I don't see them. They're not there. What should we do next? Next thing, well, let's go right back to the computer. go to the computer, see if the signal's getting there. Maybe we have an open in the harness somewhere, right? Remember how we talked about opens? So maybe we have an open in the harness. So let's check back at the computer at the connector and see what happens. Check the crank sensor, crank, crank, crank. All good there. Check the cam sensor, cranked it over. All good there as well. So we've established that the cam and crank sensors are functioning properly because we tested them directly. And we also verified the signals are getting to the PCM. So I don't have a harness problem in this situation either because the signals are making it all the way home. The PCM, though, tells us due to the data that it's not seeing the signals from the sensor. So it sounds like the signal path is good up to the PCM, but the signal's not getting in the PCM. So there's some sort of an internal failure somewhere inside there. So this vehicle needs a new PCM. If we'd only relied on that scanner data, what would we have done? Well, maybe we may have replaced that cam and crank sensor again. Maybe we would have went with ignition. Maybe we would have went with fuel. Hard to say. How long would it have taken to get to the same conclusion that it needed an ECM? All right. In this case, it took about half an hour or so to go through it. You had to put it up in the air to get to the crank sensor. So it took a little while, but about half an hour to get to the point where, yeah, this thing needs an ECM. There's really nothing else it could be at that point, right? So verify the component, verify the signal path. If the component's good, the signal path is good. There really isn't much left, right? So that's how we arrived at that conclusion. I thought that was a nice little, it's a little different, right? That's not your usual necessarily no start issue. So I thought that was kind of a interesting diagnosis. So let's talk guided component test before we go live on the tool and show you some of these things in real time. So as we saw in the material there, it gives us operation, location, connector views, tech notes, and anywhere from 1 to 6 testing methods depending on how the component is set up. So those testing methods could be low amp probe testing, do a current ramp, analog testing, that's anything with a varying voltage, digital testing such as frequency, time base, CAN bus, secondary ignition testing, pressure testing, basic electrical testing like an alternator ripple test or a voltage drop test. Right? All of those things would be available depending on the component. All of that leads us to avoiding unnecessary parts replacement. If we're testing the component itself and it tests good, we don't need to replace it, right? Because it's working, it's something else. So we don't need to unnecessarily just replace the part just because. We can actually test it and confirm that it is the problem. In turn, that'll help us prevent comebacks for misdiagnosis, right? Oops, I put that part in and that didn't fix it. It's something else. Also prevents the loss of a customer. So if they did have a problem, maybe they came back once, maybe they didn't come back, maybe they never came back. Those are the worst ones, right? Where it's not quite fixed right, but they just decide to go down the road instead and see if another shop can fix it. And maybe they do. And maybe that shop down the road fixed it, right? And then they gain that customer as that shop, right? Also, the other side of that coin could help you attract new customers, right? So if you get known as the shop that, hey, they tested it right the first time and they go through and they do a really good job with that, then maybe you get new customers based on that reputation. And all of those roll up into helping the shop's profitability. Whether you're a shop owner or a technician, I think you'd agree having a profitable shop is better than a not profitable shop, right? Because the shop's not profitable, you might not be there very long. All right, so we want to have profitability in our shops that helps everybody in turn over time. Okay, so let's go with our live walkthrough. So if you're joining us late, if you're on Zoom, if you have any questions throughout this presentation on anything we cover, just go to look at your Q&A box, click on that Q&A button, and I'll be able to take a look at those at the end. If you're watching us live on YouTube, please use the chat feature. I'll be able to see those questions in chat as well as we go through at the end. So let me pull up my tool here. Okay. And let's go into and start talking about these guided component tests. All right, so it's right there on the screen. So this is available on any of our tools that have the lab scope function. So Veris, Zeus, Modus, Triton, and Vantage. So we go in there, I need to load a database. So it's our North America database. And then we get to our list of vehicles, or list of makes, to be more specific. So 28 different makes are covered. And as I said earlier, it goes back to 1981, and there's over 5 million tests available. One thing I'd like to note before we ID a vehicle, at the very bottom here, we have this little button that says training and classes. So there are hundreds of built-in training and classes inside this tool as it sits right here. So there's over 65 categories of class with additional pages underneath that as well. All right, so let me talk through there's 3 different sections in this training classes. So we have power user test first. So this would be if you're a bit more of an advanced scope user, maybe you're a little more familiar with it, or maybe you just want to do a more advanced test as you learn how to use the tool a little bit better. We have various current probe tests, dual channel tests, secondary ignition tests, and pressure transducer tests. Now, these are more of a generalized test or generic test, should I say, not vehicle specific in this case. So these are just let me just go into dual channel test, show you some examples like CAN bus test, crank and cam relationship test, throttle position sensor 1 and 2 for like a drive-by-wire vehicle where they have 2 sensors there, right? So that is power user test. Next section is features and benefits. So this is things like a 5-minute walkthrough with the demo board. So as you're familiarizing yourself with the tool, perhaps there's a few different demo boards that we have. You can use one of those. You clip on to certain places and you can get different automotive signals right to the tool without having hooked to a car. Product descriptions and accessories. So accessories are things like ignition accessories, pressure transducers. How about a low amp probe? So we go in here and select any of these. We get a picture and a part number. So next time your friendly neighborhood Snap-on dealer comes in, say, hey, I'd like a low amps probe, and here's the part number. Would you get me one? And I'm sure they'd be more than happy to get you one. They may even have one on the truck. You never know. All right. And then last section is how to. Now, I saved this to last because this is where the bulk of the information is inside training and classes. So you see we have 65 categories here. So we have evap class, mass airflow calculation class, running compression waveform class, hybrid vehicle class, immobilizer functions. Let's see, brake electronics, common rail diesel injection, electrical theory explained. All right, if I go all the way down to the bottom, I have test tips. So under test tips, this is just one of the 65 categories. There's 13 different articles underneath test tips by itself, right? So each of those categories will have multiple articles underneath it. Just, you can, at your leisure, just go and you don't have to connect to a vehicle. You can do it wherever, as long as you have the tool in front of you. You can go in and you can just read through and increase your knowledge, right? It's always good to increase your knowledge, especially when it comes to automotive theories and such. So that is built right in. So I figured I'd let you know because we don't really, we haven't really talked about it so much. It's actually been in there for quite some time. We just made an enhancement in the last couple updates. So we increased by a large margin how much information is in there, but it's been in there for quite some time. So training and classes have been enhanced, and it's definitely a good thing to check out. Okay, so let's walk through a couple of tests on guided component tests. I'll walk through a couple different signals for you. So once again, VIN specific. So we'll go into BMW because I have a BMW demonstration board here. So we'll go to BMW. It's 2012. It's 328i. And it's this engine right here. Okay. Confirms our vehicle. We hit OK. Once we've done that, we see our list of systems. So in this case, we have 4 systems we have information on. So we'll go to engine. Here's our list of components or subsystems on this vehicle. And I want to go to a cam sensor. 2 cam sensors on this vehicle. So we have exhaust and intake. I'll go to exhaust. And let's look at some component information. Let's see how it works. Okay. So it is a digital camshaft position sensor. So it's a Hall effect type sensor used to detect rotational speed and position of the camshaft by interpreting a reluctor wheel attached to the camshaft. By the way, quick little preview for next week. We're going to talk at length about Hall effect sensors and how they work. So if you want to join me next week, we'll talk more about that then. It produces a digital voltage signal pattern based on the reluctor wheel. This can be observed at the sensor. All right, both cam sensors are a 3-wire Hall effect switch. One is for the intake, one is for the exhaust. And then over here, it tells us our connector view. We will tell you where we're looking at this connector because I get questions on this every once in a while. So how am I looking at it? Am I looking at it unplugged? Am I looking at the sensor unplugged? Am I looking at it from the harness? More often than not, it'll be from the harness side back probing because we want power applied, we want ground applied, we want signal applied. Now, sometimes we will have you disconnect and we'll say disconnect it at the terminals itself. That's usually for like a resistance test, something of that nature. But most times it's going to be harness side back probing. What we'll tell you right there. And then we have our pinouts, 1, 2, 3, and then what wire color is associated with that. If there's an alternative test location, we give you that there as well. Back up, and let's go to that signature test. Remember how I like that signature test. Top left, remember we have color-coded leads on this vehicle. I keep trying to highlight that, and it's not going to work because it's not on PowerPoint. But yellow goes to cam signal. So that is, let's see, cam signal is number 1. So right there. Black to a known good ground. Now, we don't want to necessarily use the sensor ground because we want to make sure it is a good ground, because the sensor ground could be the problem, right? We could have an open or something of that nature in the ground side. So we want to make sure we're going to a known good ground, block, body, or battery. We hit view meter. Click, click, buzz, buzz. It automatically sets the voltage range where it needs to be, and automatically sets the time base where it needs to be. All right, so really all we need to do is hook up a couple wires, and we should be able to test this component. If I scroll up a bit, I see my known good pattern. All right, so let's see. Should be a 5-volt square wave. It'll start with one short pulse, then a long square wave, and we'll finish with a medium length square wave, and then repeat. So we have a short, a long, and a medium. Right, so 3 different sizes, looks pretty darn close to the same. 5 volts on top, 0 volts on bottom, all is well. So if I see this, they match, that's a good pattern. I chose this one specifically because it also gives us a known bad pattern. So if we suspected we had a bad cam sensor and we hooked up to it and we saw this pattern, well, that's a bad pattern. On all signature tests, it will give you a reference or a known good or a known good pattern. Right, so if it's just a volt, you should see 5 volts, then it'll just be 5 volts. It won't show you a picture of that. But if it's some sort of a picture like this, it will show you a picture. If we happen to connect to a bad car, then we will give you a known bad pattern in there as well. So I thought that was kind of cool when I found that. So we got the known good there, we got the known bad there. Either way, if it looks like this, it's not good. Right, easy enough. Okay, so that's a cam sensor signal, fairly common digital 5-volt square wave. Every vehicle is a little bit different, but a lot of them use that 5-volt square wave. Now let's go into fuel system. Let's pull up the fuel injector. This one uses a pretty standard fuel injector that you'd be able to see on many types of vehicles. So it's a good representation, I guess. So we're going to component information. So it's a conventional gasoline fuel injector, right? Because we have multiple different types of fuel injectors out there nowadays, but this is just a conventional gasoline fuel injector. So these are normally closed solenoids responsible for delivering atomized fuel into the intake manifold ports. When energized, the coil winding inside the fuel injector will create an electromagnetic field. This will pull the pintle off the seat and allow the injector to spray fuel. All right, so if we think about the inside, we have a little pintle, and that's kind of like a valve. When that pintle is sitting on the seat, no fuel can spray. The electromagnet's on the other end of that pintle, and when it energizes, it builds an electromagnetic field, pulls that pintle up, then fuel can spray past the pintle. When it closes the valve. Also to know, ignition positive is supplied to the injectors by the fuel injector relay, and the PCM switches the injector ground sides using what we call the injector driver, pulls that down to ground, and that's what turns it on. Looks like the best place to test it is at the ECM because it's probably hard to get to the fuel injectors in this case. So we'll back up, and let's go to that signature test once again. Yellow to injector control signal for whatever injector we're testing, black known good ground, and we'll hit view meter. Once again, sets the voltage range where it needs to be, sets the time base where it needs to be for us. If we pull up, here's my known good. There's my picture right there. It looks pretty darn close to me, right? So in that case, we would imagine that is a known good injector. I want to talk about this note though. May need to raise the voltage level if the signal is clipped. So in this case, we look at the very top of that. That is not on the screen, right? That's off the screen. Is it here? Up here? I don't really know where it is because I can't see the top. Now, the thing about guided component tests is it gets you in ballpark in the neighborhood where you need to be. Most of the time, it'll be spot on. You don't have to worry about it. In cases like this, where we could have a signal going higher than where it's set, that's fine. We can adjust this. All right, so in order to adjust this, we can. Some folks think that, oh, well, it's just, it's simple, easy scope, and, it just sets it where it is and you can't change it. And that's not true at all. We can do any setting changes in this that we can do inside the graphing meter or inside the lab scope. So in this case, I'll show you how to do that. So we'll go to meter, and that just makes it easier to see my settings in a minute. Go down here on the right-hand side, click once, I get my measurements. I click again, I get my settings. If we look over here on the left where it says profile, this is where I could add additional channels to my signal. So if I wanted to test more than one thing at a time and see how they compare over time, on my Veris and my Zeus, I can have up to 4 channels on the screen. On a Modus Triton or Vantage, you can have up to 2 channels on the screen, so you can compare 2 things at the same time. So in this case, I want to look at one thing, so I'll turn the rest off. Next thing is probe. So probe will tell the tool what we have connected to it, what type of signal we're reading. So in this case, test lead volts. Right, so we know that we're testing voltage. We'll leave it there, but it could be vacuum, pressure, low amps probes, ignition probes. Next one's peak detect. What this does for us is it removes any filters, any buffers from the signal, sets the scope to maximum sample rate. So we're able to catch teeny tiny little microsecond, fraction of a second glitches in the signal if we need to do so. Gives us extra detail, say with an ignition pattern. Next one is filter. So if I have some sort of an RF type noise waveform, it's really, really noisy. Maybe I got a bad ballast in a light in the shop, or I don't know, some maybe CB antenna out back, or I don't know, whatever might cause high RF. This will allow you to filter that out and give you a nice clean pattern. Another good example where you might want to use that is, say, on a low amps probe. Low amps probe are very susceptible to noise, and just if you get a noisy pattern, just click filter, it'll filter it out. Inverted, we'll flip the pattern upside down or right side up, depending on your point of view. That's also handy for low amps probes, because low amps probes are directional. I don't know if you ever noticed, if you take a look at where the circle is, the little loop that goes around, it's got an arrow on it. Right? If the amperage flows in the direction of the arrow, I will get a positive number. If it flows the opposite direction of the arrow, I will see a negative number. And it's thicker on one side than the other, so maybe I can only fit it down in that hole just one way, right? And then I get a negative number. So if I hit invert, just flips it over, it gives me a positive reading. That's all it does. It's like -5 to +5 is what it would do. Coupling AC. Now, if there's some sort of an AC type component to the waveform, it strips out the average and amplifies those differences up or down. Just makes it easier to see if there are differences in the pattern. Then we get to scale. So in scale, that allows us to change the size of the window. How tall is this window? So right now you see it's set to 50 volts. So that means I have 0 volts down here on the bottom, and it's 50 volts on the top. The reading's off the screen, but that'd be 50 volts from here to here, right? That's a 50 volt range. So let's click on that and we'll change it. So let's see what happens if I go to 20. Well, that just made my problem worse, right? Because now I'm only looking at 20 volts. Our signal was at least 50 volts at the top, maybe more. So now we're only looking at the first 0 to 20 volts. So that doesn't help us. 50 volts is where we started. Let's go up, next one up to 100. So go to 100. There we go. Now it looks like the signal got cut in half, right? It's half as tall as it was before. The signal hasn't changed. The signal's still right at 50 volts, right? There's 50 volts there. There's 50 volts right there. It's a little bit over 50 volts at the very top, perhaps. But now I have this extra 50 volt headroom on top. So I have an extra 50 volts above that in case I do have a higher spike that I need to see or I need to catch. I always like to have a little extra head on the top just to be sure I don't get one of those spikes. I don't want to miss it. Right? So having that extra headroom is not a bad plan. So we change our scale. We can also change our time. So that's the width of the window. How much time is passing as we're looking at the signal. So if I click on down here, it's set to 10. Let's see what happens if we go 10 times that. Let's go to 100. 100 looks like it squished it way over in the corner there because there's 10 milliseconds, right? And then up to 100 milliseconds over here. So this is 10 times as wide as we were before. What if I go down to 2? Well, 2 milliseconds, it almost takes up the entire screen, right? I got this whole big gap there. When I'm making these changes, that pattern is not changing. The voltage isn't changing. Whatever's going on with it is not changing. I'm just changing the size of my window. Am I getting a closer look? Am I looking further away? So in this case, I liked 10 milliseconds. That was pretty good. So we'll leave it there. So that's our vertical, that's our horizontal. And then we have one other thing we can adjust here, and that is our trigger points. That's this plus sign right here on the bottom left. What this does for us, it does a couple of things for us. So whenever the voltage passes by this plus sign, wherever it crosses, it will start drawing the picture of that pattern from wherever that is. So that allows us to do a couple things. So if I see how it's way over on the left, maybe I want to see what happened before this. I want to see some more of the pattern before this. So all I got to do is grab it, move it over somewhere in the middle. Now I can see what's going on before it happens and after it happens. Right. So all that does is allows us to move it horizontally like that. The other thing it does is watch when I move it outside of the pattern, way up in the top, nothing going on up there. It disappears. Also says waiting for trigger on the right-hand side. That means it's waiting for the signal to pass trigger. There it was. It just popped on for a second. So this is a pulse. Fuel injector is a pulse, right? It happens periodically. It's not a constant signal like a cam sensor or crank sensor, right? It happens every time it fires, but it's a pulse. So when that happens, if it pulses at the same time the screen refreshes when it pulses, then you'll see it on the screen. If it doesn't, we need some way to capture that. So that's what our trigger does for us. We put it down somewhere in that voltage. I'm around about like 10 volts right here. And then every time it happens, it displays it on the screen every time it pulses. All right. Now I have it on the screen. Now I'd like to, once I have it on the screen, I'll take a look and see what's going on, voltage-wise, time-wise, analyze this. So in order to do that, I need to turn on my cursors. So that's up here on the top. Click cursors, click show, click back. There they are. All right. So I'm going to set it up like this. Now there's two hard and fast rules with the scope. Rule number one is I cannot change any of these settings unless it's recording, and it records by default, so we don't have to worry about that. The other thing is I cannot make any measurements on this until I stop recording because it wants to measure a static picture. All right, so I got to go to the left down here, stop. And then I also need to change my screen view on this tool. Modus Triton Advantage, it has all the measurements and everything else on the same screen on the Varus and the Zeus. It gives us these extra screen views here. So you see on the bottom right, these are my measurements. So I have cursor 1, cursor 2, and delta. So cursor 1 is going to be where do these two lines meet? So this yellow number says 17.2 volts. Now, if we remember back to our component information, we read up that it said a supplied battery constant, and then the computer grounds it, right? So battery constant, I should see what, 14 volts, 14.4, somewhere in that neck of the woods, but I'm seeing 17.2. Now I'm going to chalk that up to my simulator board, putting out that much. But if I saw this in real life on a real live car, first thing I'd go straight for that alternator and see why am I overcharging, right? So an overcharging situation could cause all sorts of other drivability problems in a vehicle. So really, if you suspect that's a problem, check that first because that could eliminate a lot of your other problems. But in this case, in this scenario, let's just say that that's fine, okay? Just for our argument's sake in this presentation. So voltage comes in. And then we said that the PCM grounds it, right? So it pulls down to ground. I should see round about 0 volts here. I'm seeing negative 0.1 volts. That is really close to 0, right? With a tenth on either side would be good. And then delta will give us the difference. So that minus that is that, right? So it's a double negative because it's a negative number. So 17.3 is the difference between those two. So that is our vertical measurement. We can do a horizontal measurement too. So let me take number 1, put it there. Number 2, put it there. Let's see how long that injector is fired. All right, so that'd be our injector commanded on time or commanded pulse width. When I'm measuring time, I'm using the white numbers on the bottom here. The first two just tell us how far away from this 0 point in the bottom left-hand corner is the cursor. I want to measure something time-wise. I put it in between the two cursors and then use my delta time. So in this case, this on time is 1.27 milliseconds. Great. Voltage comes in, grounds it for a set amount of time. What do we talk about? Where do we learn about how this thing works? Well, it's got the pintle and it has the electromagnet, right? Now that electromagnet is a coil of wire. It holds it open using that electromagnetic field. While it's being held open, that coil is collecting all that voltage flowing in there. Works just like on the same principle as an ignition coil. When that ground is released, the pintle closes, all of that stored energy in that coil has to go somewhere. Can't just disappear. So it gets induced back into the line. So that's why we get that spike at the top. So let's see how high this spike goes on this one. So in this case, I'm seeing 49.6 volts. 17 in, 49 out, that's more than double. And I guess that's fairly standard, right? If I do this on my car, I get about 72 volts usually at idle. I did it on a Ford Fusion one time, got about 90 volts. don't be concerned about a large number over there. Is basically what I'm trying to say, because it's normal. It's designed for it. What you want to be concerned about, and I can't tell you what normal is either, because it has way too many variables. How much voltage is going in? How long is it being held open? How many windings are in the electromagnet? All right, all of those things are variables for this. So what good is say you measure all the injectors on a vehicle. Are they all pretty close? If they're all pretty close, you don't really need to worry about that part of it. If one's way higher or one's way lower, that's the one you want to look for, right? Where is my outlier? Where is my odd man out? That's where you want to look. And that's the beauty of being able to use the component tester or the scope, so I can see a picture of what's going on with my component, right? And with that, that is our time here today. So make sure you tune in for new diagnostic content every week. We will be premiering a new video every Wednesday at 7 p.m. UK time. So make sure you check it out on the YouTube channel. If you're watching, well, of course, you would be watching this on YouTube, but make sure you subscribe, thumbs up, ring the little notification bell so you know anytime we post new content. And it's youtube.com/SnapOnDiagnosticsUK. With that, time for questions. If you have any questions, just feel free. Once again, if you're watching this on a premiere, just leave it in the live chat and we'll answer those. Otherwise, leave a comment under the video and we will get to those as we monitor those comments as well. So I'd like to thank you for taking a little bit of time out of your day to learning a little bit more about how you might be able to be more efficient at diagnosing vehicles using some of the information that we've given you today. Hopefully we'll see you next week. Hopefully you can watch and see you on any of our other videos. Have a good week, have a good night, and take care.